Consider a metal conductor. Current in a conductor is due to the valence electrons in it. The valence electrons are not bound to any particular atom and are free to move about within the volume of the conductor. These electrons are called the conduction electrons. Rest of the conductor is made of relatively heavy positive atoms that are referred to as the lattice. Let us consider a conductor that is not connected to any battery or to a cell. Hence, there isn't any electric field. The free electrons move at random, collide within themselves and with the ions in the lattice. The radius of an electron is very small as compared to that of an atom. Hence, the collisions between conduction electrons and other electrons are neglected. As the conduction electrons move at random, they have different velocities in different directions. Let the velocities of the free electrons at any given instant be u1, u2, and so on up to un for n number of electrons. As the directions of the velocities are random, the vector sum of the velocities of all the electrons is equal to 0. Hence, the average velocity of all the electrons at the instant u is equal to 0. Let this be equation 1. The motion of these free electrons is called thermal motion, as the motion of these electrons depend on their average kinetic energy. Average kinetic energy of the electrons depends on the temperature of the conductor. Since the average velocity of the conduction electrons at any instant is 0, there is no net transport of electric charge. Thus, there is no net electric current through the conductor. Now let us consider a conductor connected to a source of electromotive force, such as a cell or a battery. When the conductor is connected to an external source, an electric field is applied across the conductor. Due to the electric field, the free electrons are accelerated in the direction opposite to that of the field. The magnitude of the electric charge on an electron is E. If E is the magnitude of the applied electric field strength, the force on the electron F is equal to E into E. If m is the mass of the electron, then the acceleration of the electron A is equal to the ratio F to m, which is equal to E into E by m. Let this be equation 2. Due to the acceleration, the free electrons gain velocity and hence kinetic energy. With the acquired kinetic energy, the free electrons collide with the atoms within the conductor. During such collisions, the electrons give up their energy to the atoms. Hence, their velocity decreases. Immediately after the collision, the free electrons are accelerated due to the applied electric field. This acceleration gain increases the velocity and thus the kinetic energy of the electrons. The electrons again collide and lose their kinetic energy. Due to these repeated collisions, the average acceleration of the electrons is reduced to 0. Hence, the average velocity of the free electrons is constant and is directed opposite to the direction of the applied electric field. The average velocity gained by the free electrons in a conductor when subjected to an electric field is called the drift velocity. Let us find an expression for the drift velocity of the conduction electrons in a conductor when subjected to an electric field. Earlier, we considered the velocities of n number of conduction electrons at any given instant to be u1, u2, so on till un. Now, when the electrons are subjected to the electric field, let their velocities be v1, v2, so on till vn. Here, v1 is equal to u1 plus a into tau 1, where tau 1 is the time between two successive collisions of the first electron. Similarly, v2 is equal to u2 plus a into tau 2, where tau 2 is the time between two successive collisions of the second electron. So on till Vn is equal to un plus a into tau n. The average velocity of all the free electrons is equal to the drift velocity Vd. Hence, Vd is equal to V1 plus V2 plus so on plus Vn divided by n. Substituting the expressions for V1, V2, so on till Vn in the expression for Vd and simplifying, we get Vd is equal to u plus a into tau. This average time elapsed between two successive collisions of a conduction electron is called the relaxation time. It is of the order of 10 power minus 14 second. This implies that an electron is free from any collision for the duration of 10 power minus 14 second and is relaxed. The mean distance travelled by the electron during the relaxation time is called the mean free path. Let L be the mean free path of the electron. Then we get L is equal to drift velocity Vd into relaxation time tau. Hence, we get Vd is equal to L by tau. Let this be equation 3. We also get L using the equation of motion, S is equal to ut plus half at square in kinematics, where S is the displacement, u is the initial velocity, a is the acceleration, and t is the time. From this equation of motion, we get L is equal to half a into tau square, where a is the acceleration of the electron. Substituting the value of the acceleration from equation 2 and simplifying, we get L is equal to half e into e by m into tau square. Let this be equation 4. Substituting the value of L from equation 4 in equation 3 and simplifying, we get Vd is equal to half e into e by m into tau. Let this be equation 5. From equation 5, it is clear that the drift velocity of the free electrons is proportional to the electric field strength E and the relaxation time tau. Equation 5 can be further simplified to get Vd is equal to k into E, where k is a constant equal to E tau by 2m. Let this be equation 6. The constant k depends on the material of the conductor and its temperature. Let us now find the relation between drift velocity and current density. We know that the magnitude of the current density, denoted by J, is defined as current per unit area considered normal to the current in a conductor. Consider a cylindrical conductor whose cross-sectional area is A. Let the conductor be connected to an electric source Let E be the electric field due to the source. If Vd is the drift velocity of the conduction electrons in the conductor, then the net distance travelled by the free electrons in the conductor during the time interval delta t is equal to Vd delta t. The volume of the portion of the conductor through which the free electrons travel during time delta t is equal to A Vd delta t. Let n be the number of free electrons per unit volume of the conductor. Then the number of free electrons within the volume considered is equal to n A Vd delta t. All these free electrons cross the area in time delta t. Hence, the charge crossing the area A in time delta t is given by delta Q is equal to NA Vd delta TE. Let this be equation 7. From equation 7, we get current through the conductor I is equal to delta Q by delta T, which is equal to NA VDE. Hence, the magnitude of the current density, J, which is equal to I by A, can now be written as equal to NVDE. Let this be equation 8. Substituting the value of Vd from equation 5 in equation 8 and simplifying, we get the magnitude of current density, J is equal to Ne square tau by 2m into E. The magnitude of current density, J, is also written as equal to sigma into E, where sigma is a constant called electrical conductivity of the conductor, which depends on the nature of the material of the conductor and its temperature. Thus, sigma is equal to Ne square tau by 2m. Let this be equation 9. The reciprocal of conductivity is called the resistivity of the conductor. It is denoted by the Greek alphabet ρ. From equation 9, resistivity ρ is equal to 2m by Ne square tau. Let this be equation 10. For a given material, N remains constant. The mass m and charge E of an electron are also constants. Hence, from the equation 10, it is clear that when the value of tau decreases, ρ increases. This implies that as the relaxation time decreases, number of collisions of free electrons increases. The collision of the free electrons with the atoms of the conductor restricts their flow, and this causes resistivity of the conductor. Similar to resistivity, another important property of conductors is mobility. Mobility is denoted by mu and is defined as the magnitude of drift velocity per unit electric field. Thus, mu is equal to Vd by E. Substituting the value of Vd from equation 5 and simplifying, we get mu is equal to E tau by m. Its unit in SI system is meter square per volt second.